Here's a brain teaser. Suppose you have a can of Coke and a can of Pepsi. The Pepsi is at 0.01 degrees centigrade. It's still liquid, close to freezing, but it's not quite there yet. And the can of Coke is at 99.99 degrees centigrade. Not quite boiling, but close. Let's assume that you have the exact same amounts of each, and let's assume that they're chemically identical. I know the marketing departments of the respective companies wouldn't agree with this, but let's just say to a first approximation that's true. What is the maximum temperature to which you can heat up the Pepsi using only the heat from the can of Coke? Think about this for a second. While you're thinking about it, let me tell you why I love this riddle. Most riddles are just throwaways. But when you have the answer to this particular riddle, you will see the answer all over the place, not just in human engineered devices, but even in, more commonly, in biological systems. Okay, keep thinking about it for a second while we do the title card. So hopefully you did not guess 50 degrees, because that is not the right answer. Well, I guess it would be the right answer if you were placing limitations on the question that I didn't actually require. So if you assumed that I meant you could only use the aluminum cans that the liquid came in during the problem, then yeah, that would be true. You just stick the can of Coke next to the can of Pepsi, and they come to thermal equilibrium. Heat passes from one to the other. But all I said is that you can only use the heat from the liquid inside the cans. I didn't say you have to use the cans themselves to transfer the heat, or that you weren't allowed to use different containers, or transfer liquid between containers, or divide and remix, or even use tubes or manifolds or other devices to transfer the heat. So with that hint, I bet you're starting to see what I'm getting at. Now we're going to assume here that the cans themselves are perfect conductors of heat, and that no heat is transferred to the surrounding air, just through the cans when they come into contact. We established that if you just use the two cans, 50 degrees really is the best you can get. But let's suppose you divide each can by pouring it into two cans. Then you take two of the smaller cans and put them into contact. They each go to 50 degrees. You then shift the cans over and let them come to equilibrium again. Now shift them over a third time and let the final two come to equilibrium. So the result of this is that two of the cans are at 50 degrees, one can of Pepsi is at 25 degrees, and one can of Coke is at 75 degrees. So then if you recombine these fractions, then we'll end up with a temperature of 37.5 degrees for the Pepsi and 62.5 degrees for the Coke. So we're already doing better than the 50 degrees. Now it probably seems pretty straightforward what you do next. Instead of 2 cups, let's do 3. Or 10. Or 100. Well, we're not going to wait for that one to go completely. You might say it's not really practical to subdivide this into thousands of tiny cups, but of course we don't do this in practice. Let's get rid of the cups entirely and just have a thin tube that drains each can, and the two tubes flow in opposite directions, separated by a thin divider that allows heat conduction, and then deposits the liquid at the other side. If you make this pipe infinitely long and thin, and assuming that the divider is a perfect heat conductor, you can transfer all of the heat. So the answer is that in this infinite limit, you can completely flip their temperatures. You can heat the Coke up from 0.01 degrees centigrade all the way to 99.99 degrees centigrade, and the Pepsi goes in the opposite direction. This is called a countercurrent heat exchanger, and while obviously you can't have an infinitely long tube, you can make all sorts of designs that get pretty close to approximating this and can successfully exchange almost all of the heat. Here are some types. The easiest thing to do is to just use 2 concentric tubes, but more commonly you'll see rows of parallel plates or tube and shell designs or spiral designs. There's really quite a variety depending on the exact situation and the practical limitations. Obviously, in the real world, there will be limitations on how large it can be, how expensive it can be, practical manufacturing limitations. 3D metal printing is really interesting in this area because it allows you to execute some optimal designs that are otherwise impossible to manufacture. But that's a digression. I won't get into that. You also have to think about more prosaic things, like how do these things get cleaned, and how do they handle high pressure, all kinds of stuff. And that's why there are a lot of different designs that are all getting at the same basic principle. Now, this is useful in all kinds of situations. You see it a lot in the chemical industry. Suppose you have some chemical reaction that requires a certain temperature. You need to heat up the reactants, let them react, and then cool them down again. You don't want to spend the money on energy to heat up every liter to the full temperature just to waste that heat energy after the reaction is done, cooling the reactants down. Instead, you feed the reactants into the reaction chamber through a countercurrent mechanism that preheats the reactants using the heat from the products. You recover or recuperate the heat, and you only have to add a tiny fraction of the heat you would otherwise. I'm sure you can imagine there are a lot of places that these could be used, and many of those places they haven't become common yet. But as standards for energy efficiency go up, by necessity, you're going to see these pop up in new places. Like, for example, suppose you have a house. You need to let in some fresh air into the house and let the stale air out of the house. Otherwise, you'll get a buildup of carbon dioxide and odors. In a leaky old house, this just happens naturally, and you don't need to worry about it. But if you've ever paid to heat an old house, you know that this is not a great system. But if you seal up the house really well, you're going to need to actively move some air in and out, and that's going to bring in some air at the outdoor temperature. Now, this isn't a problem in the spring and fall when the temperatures are very mild, but in the winter, that fresh air is cold, and the warm air you let out into the ambient environment is nice and warm, so you'll be running your furnace more than you should be. And in the summer, it's going to be the same, except for your air conditioner. But if you exchange the air through a countercurrent mechanism, you can get fresh air at room temperature and much lower heating bills. This is how the hyper-efficient passive houses do it, and I think you'll see this more going forward. So these are applications and things that humans build, but you see this even more in the natural world, which is not surprising given that the natural world operates under much more significant energy constraints than human-designed contraptions in the industrial age. Inefficient plants and animals just don't last long. So you see this exact mechanism in heat conservation in animals. Blood vessels near the skin do countercurrent heat exchange so that you don't lose a massive amount of heat through your skin when it's cold outside. Birds use these vessels in their feet to avoid losing huge amounts of heat through their long, thin legs that are dipped in icy water. I hope you can start to see why I like this riddle so much, because this is a pretty general concept that shows up all over the place. But it's actually even more general than this, because it doesn't just apply to heat, but rather anything that can flow across a membrane to reach equilibrium. Suppose instead of liquids at two different temperatures, we had liquids with two different levels of salinity. Instead of Coke and Pepsi at different temperatures, you have, say, salt water and fresh water. And suppose that instead of being separated by a thin sheet of metal that conducts heat, it was separated by a thin membrane that allowed sodium and chloride ions to pass through. You could, in theory, transfer all of the salt from the salt water to the fresh water. All of it. And this gets used in biological systems. Your kidneys use countercurrent exchange mechanisms, and if they didn't have these, you would be unable to concentrate urine. The most concentrated you could get your urine would be the same salinity as your blood, which would be a big problem if you were walking through the desert for a few days. The two fluids don't even need to be both liquids. Suppose one is, let's say, nitrogen gas with some oxygen dissolved in it. That sounds like our atmosphere, right? It's just air, a 20% oxygen solution. And suppose the other one is a liquid that can easily dissolve oxygen due to some additives. That sounds a lot like blood. Oxygen is not terribly soluble in pure water, but it's quite soluble in blood due to hemoglobin. And suppose they're separated by an oxygen-permeable membrane. Well, that sounds a lot like lung tissue. Obviously, from what we've seen, the best way to get the dissolved oxygen in the atmosphere to the blood would be to use a countercurrent mechanism. And now here's where things get really interesting. Not every organism has a countercurrent mechanism in their lungs. Some do and some don't. Insects don't. They just rely on passive diffusion through lungs in their legs. Mammals and reptiles don't either. They have what's referred to as a tidal system that just involves inhaling, waiting for equilibrium, and exhaling. This is like the equivalent of just letting the can of Coke and the can of Pepsi directly touch and equilibrate. Now, in a tidal system, you can increase the amount of oxygen you get to some extent by hyperventilating. This would be like equilibrating the single can of Coke with 10 cans of Pepsi. But that comes at the cost of having to use a lot of energy to pump air in and out. When people get advanced lung disease from emphysema, for example, you often notice them getting really, really thin. That's because they're doing a tremendous amount of work hyperventilating, trying to keep their oxygen levels up. Now, fish, on the other hand, do have a countercurrent mechanism to exchange oxygen via their gills. A tidal system for them just would not do because water is much, much more viscous than air. When humans breathe, they move about 500 milliliters of air back and forth, and that's not really terribly difficult or strenuous, but moving that much water back and forth would be a big deal in terms of energy. Birds also have a countercurrent exchange mechanism that's a little bit more complicated. Now, it's true that they only have one tube for air to go in and out, the trachea, just like mammals and reptiles, but they use pairs of air sacs that inflate and deflate and allow the airflow through the lungs to be unidirectional. Because of this, birds can do things at high altitude that other animals couldn't dream of. For example, there's a species of bird, the bar-headed goose, that migrates over Mount Everest. Now, mammals not named Reinhold Messner cannot do anything like that. I remember seeing a nature program talking about how high in the Andes Mountains the pollinators are birds rather than insects, and how remarkable it was the birds could thrive in such a harsh environment. And I thought, what? That's exactly what you'd expect. Birds have a respiratory system which is much more suited to high altitudes than insects, so you would expect that they would dominate in an ecological niche at high altitude. At low altitudes, where there's plenty of oxygen, insects have other things going for them, and they tend to dominate in that niche. But for high altitudes, birds are going to be the dominant species. So I really like all the biological applications of this riddle, but I'll also tell you the last reason I really like this riddle, and that's because it teaches a very subtle lesson about the laws of the universe. So to get really profound for a second, you can ask, well, what is time? Well, in mechanics, there's really nothing that indicates that time is moving forward. If you watch the planets going around the sun and fast forward 1,000 years, you can't really tell that any time has passed. Or if you have a frictionless pendulum that never loses any amplitude and you took a video, you couldn't tell what time the video was taken, whether it was taken sooner or later, or even if it was playing backwards. But as soon as you introduce friction, you could absolutely tell. If you drop a steel ball on a perfectly hard surface and it bounces with no friction and keeps bouncing again, you can't tell if the video is going forward or in reverse, or whether it was taken on the first bounce or the 100th bounce. But if you drop an egg on the floor, all that kinetic energy gets converted to heat as the egg splatters on the floor. You can definitely tell what came first and what came second. So in all these cases, it seems like the thing that makes time happen is the involvement of heat, the flow of heat. And that's sort of nibbling in the right direction, but that's actually not the whole story. You can see this from the theoretically perfect countercurrent heat exchanger. You can imagine if I had this perfect heat exchanger and I used it to flip the temperatures, I could pour the liquids back through in the opposite direction and then just end up where I started. And I could keep doing that over and over, almost like a thermal pendulum. And like the frictionless pendulum, I would never be able to tell where I was at in the sequence, or whether I was moving forward or backwards. It would be like the whole concept of time moving forward just became meaningless. In the same way that you can't say that the x direction always increases. That really makes sense. You can move forward or backwards in the x dimension. Something similar would be true of time, because you can't really distinguish which way it's going. So the flow of time is clearly not about heat per se. You can exchange heat back and forth indefinitely and reversibly. But it sure seems to have something to do with heat. The naive guess about this riddle, just put the two cans together, that is clearly not reversible. You can definitely tell that this is time moving forward and that this is time moving backwards. But that's not true with countercurrent exchange. So what's different? How can we separate these two scenarios? Well, instead of just thinking about heat transferred, let's introduce a new quantity, which is heat transferred divided by the temperature. In the first case, say we exchange 1 joule of heat and divide that by the temperature, measured in Kelvin. It's 1 joule over 273 Kelvin, and minus 1 joule over 373 Kelvin. If you add these up, you get a positive number. If you play the video in reverse, you get a negative number. Now let's do the same for the countercurrent heat exchanger. Remember, we said that in the limit of a perfect exchanger, heat flows across the membrane, but the two are approaching the exact same temperature. So at this end, if 1 joule flows across, the quotient is 1 joule over 373 Kelvin. And on the other side of the membrane, it is also 1 joule over 373 Kelvin. So if you add those two up, you end up with 0. So now we have a hint. This quantity, if it's getting larger, time is moving forward. If it's getting smaller, time is moving backward. And things that are totally reversible and timeless don't change this quantity at all. Now, of course, if you are at all familiar with thermodynamics, you will recognize that this quantity is just called entropy, and that entropy always gets bigger as time moves forward, and that is the second law of thermodynamics.